Okay, we're going to solve problems 1 and 3 from the applying the model. We'll do it graphically and algebraically. So we've already drawn our graphs over there. What I'm going to do is redraw the V graph. So we go from 0, which is my VI, to a VF. That takes a time delta t. So there are two things we don't know here. We don't know how far we've gone during this interval, so we can solve for delta x, which is this area. This is a triangle, so it's 1/2 times delta t times this height, which is VF, which will be 1/2 times 8.5 meters per second, about 20 miles an hour, times 20 seconds, which will be 85 meters. I also don't know the acceleration. The acceleration is the slope of this graph, which is just VF minus VI over delta t, which is 8.5 meters per second over 20 seconds, which will be 0.425 meters per second squared. So we did it graphically. We can do it algebraically here as well. So here's my car. It starts at rest. It ends some ways down the road with a VF of 8.5 meters per second. The acceleration must be this direction, though I don't know what the value is. The delta x is unknown. The delta t is 20 seconds. And I have defined positive to the right. So if I want to find delta x, I know VI and VF and delta t, but I don't know A, so I'm going to pick the appropriate model that includes all those things but does not include A. And this is going to give me 8.5 meters per second times 20 seconds over 2, which is again 85 meters. Finding the acceleration, you could either just go from the definition of acceleration, or if you want to start from one of our toolkit equations, we get this, and then we'll just end up with what we had before. Okay, second problem, or problem 3 rather. So here we start off with a VI of 8.5 meters per second, and we end with a VF of 0. That all takes 20 seconds again. So if we're going to find delta x, that's this triangle again, which is the height of it is VI, times the base here is delta t, which is going to be 85 meters again. And the acceleration we can again just find from the slope, which is this time negative 0.425 meters per second squared. So that is in the opposite direction of the velocity. If we were to do this algebraically, we'd have diagram. At the end, we're at rest. So we've defined positive to the right. A must be opposing the motion because we're slowing down. Our delta x is not known. Our delta t is 20 seconds. So if I want to find the delta x, I would again use the same model. And again get the same answer. Because what we've done is switch the VI and the VF here. For the acceleration, I would do the same thing I did up there and end up with, really I'd probably just start from the definition of acceleration. And I would end up with the same thing that I had on the other side.